a constant, like this x squared plus x, something like that. So this is random. However, something like this is not random because we have an x outside the f. So there are two types of functional equations we'll be dealing with: z to z, integers, n to n, and r to n. In z to z, you have relatively more structure. So sometimes what you can do is, I mean, if everything is inside an f, you can sum the same thing multiple times, like yeah, uh, and then like multiply f of n is also equal to f of plus a plus b a1 minus a2 a2 minus a3. I mean, you get something like this, and you sum all of these, so you get m f of n equals something else. So this is maybe one way you can get a variable outside the f. But in R2R, you have to apply more non-standard techniques. I mean, sometimes you may be able to prove injectivity. So for people who don't know what injectivity is, it is f of a equals f of b if and only if a equals b. So if you are able to prove this, you get you have two things which are seemingly not equal. I mean, this is not trivially equal to this, but then you remove the f and you get these two things are equal. And this probably gives you some leverage on the question. So I will try to introduce everything via questions, and this will be more like a PSS, problem solving session. Yeah. So the first question I would like to discuss is, have people seen this question before? Okay, I'll assume not. So I'll give you guys a minute to make some progress on this, and then maybe we can share our approaches. Oh yeah, sorry. So the function is from z to z. And this holds for all integers n. Okay, so some first thoughts. Anybody? Okay, so what do I mean by P of x comma y? It's just this statement. P of m comma n refers to this statement. So I don't have to write it again and again. I'll just use the shorthand P of m comma n. So P of m comma n means you put n is equal to n. Okay. Oh, so you are subtracting this equation. Okay. Yeah. So the second one, I'll write the second one too. So putting zero is a standard thing in functional equations. Putting n equals zero, it seems like a good choice because you get sorry, I meant to put n equals zero. Yeah, we'll just write this too. So why would I put n equals zero? Because then this term and this term, these two would cancel out and we'll get probably a simpler expression. So putting n equals zero, we get n plus f of zero equals f of n plus 2014. Now this this is probably a powerful equation, and I'll number it as 1 because this means that if x can be reached via some f, then x plus 2014, x plus 2000, 2014 times 2, and so on, can be reached via f. Now what can we do? Do these two look similar? Yeah, so probably I can write the first equation using the second equation and do something after that. And do this. place this here, and then I'll write this term, the right hand side, y equals to 9. This is 3n plus f of 0. Okay, so now maybe you can guess some function which works. Anybody? Yeah, something like that. 2n plus f of 0, 2n plus some constant. Yeah, constant can be 0 too. So we'll see. We'll see if this turns out to be the case. But for now, proving injectivity seems a solid start, right? I mean, you can check the linear solutions, yeah, and you can put f of x equals ax plus b and find out the possible values for a and b, but that would not encompass the whole solution set. We don't know whether all the solutions are linear or not. Yeah, so the guys probably made thing in the f equal, and f of m equals 2n plus f of 0. Yeah, exactly. So if we prove injectivity, we can directly get the value of f. And so we take one case where f is injective, and the other case where it is not. So the injective case is pretty easy to handle. We get by this equation f of n equals 2n plus c, 2n, 2n plus f of 0. And putting this into the original equation, we can easily find out that. So let's do it. 2 times, I'll abbreviate f of 0 as c for ease of writing. 2n plus c plus n plus 2m plus c equals 2n plus c plus 6n plus c plus 1. So counting the n's, we have 4 here, 2 here, so 6 on the left hand side and 6 on the right hand side. So we can just cancel these out. And counting the n's, we have 2 on the left hand side and 2 on the right hand side. So cancel these out. What we're left is probably I made some mistake here. So I get a C out of. I get a C here too because we're doing f of n and then f of that C plus another C. So cancelling the n's and the n's. We get 2 extra C's on the left hand side and 1014 on the right hand side. 1014 is even, so and this works. So f of x equals 2x plus 107 works. F everything just cancels out in the original equation. So yeah, this is a solution. So what about the case where what about the case where f isn't injective? Any ideas? I'll write that equation. Sure. What is the simplest condition that case 2 imposes on f? What does not being injective mean? Try to think on that lines, on those lines. For some a not equal to b. Yeah. What this means is essentially f of a equals f of b for some a b such that a not equal. Try to use this condition. Okay, here's that. The original equation is sorry, I wasn't seeing the chat. It's b and we can do it n times f bounded. we don't have a period, right? Because that is for specifically chosen A and B, not for general A and B. Probably I'll put A and B instead of some M or N. M is okay. All M's are in F. Putting N equals, we can do two things here. M comma A or A comma N. This would give us, I'm doing the similar thing for B. The same, because f of A equals f of B. The same, the same. So f of A equals f of B implies f of A plus f of anything else equals f of B plus f of the same thing. This doesn't look that useful right off the bat. Probably we'll try the other thing. A comma n gives us f of A plus f of A equals f of n plus f of 3a plus 24. I'm doing the same thing for B. Now what can you put? Just write the expression, write the whole expression, and something will pop up. Yeah, we'll use that Abdul Jalil. Sorry if I'm pronouncing it wrong, which most probably is the case. We'll use that f of A plus MC equals f of B plus MC. Okay, back with this. These numbers. Okay. Oh, that is the definition of injective. Injective means we erased it. F of A equals F of B if and only if A equals B. So we have the integers here. We have the integers here. This goes to this thing goes to this thing. This thing goes to this thing. So injectivity means two from here can't go to the same thing. Like this cannot be the case. Is that okay? Okay. Okay, so I'll write the whole expression here. Do you notice the LHS in the first equation and the LHS in the second equation? They are the same.
Yes.
Okay? Because f of A equals f of B. So the right hand sides are the same, which means f of 3A equals f of 3. So we get f of A equals f of B implies f of 3A equals f of 3 implies so on. By induction f of 3 to the k A equals f of 3 to the k. Okay, so I wrote another equation. So the one marked one. This thing. Let's try to visualize what this equation means. What one means. So we take 0 here, 1 here, not 0. Let's start from 1. We go on till f of 0. Call this as one group. Next number is 0 plus 1, 0 plus 2, so on till 2f of 0. We call this the second group. These groups will go on. So what this means is the first element of the first group differs from the second element of the second group by 2014. Is this okay? Yeah. And the corresponding, suppose the ith term from this group, the ith term from this group, we are using a different color. They differ by 2014. This is because they have a difference of f of 0 and their f's, yes, they differ actually by f of 0. Their f's differ by 2014. Differs by f of 0. Differs by f of 0. But their f's, f of the ith term in the first group plus 2014 will give the ith term in the second group. So what this means is you take f of 0, f of 1, f of 2, so on, and f of 0. These are the f's of the elements in the first group. Then you continue. F's of the elements in the second group. The third group. So we can just add 2014 to every element of this group, and we get this group. The same here. Do people get this? Is there any doubt? Please feel free to speak up. I assume no. Okay. So try to think of this thing that we just concluded while keeping this in mind. Does this strike a chord? And by the way, these groups continue on the left side group. This is the first group, the zeroth group, the -1th group, and so on. So on the left hand side. What does making K large do here? Exactly. Making K large, if you take capital A to be 3 to the some large K times A and capital B to be 3 to the same large K times B. A minus B is huge, can be arbitrarily large. Not huge, arbitrarily large. It is 3 to the that we are assuming A is not equal to B. Because if A equals to B, then F is injective. This is non-zero. The mod of A minus B is huge. Mm, Now try to think how this connects to this. Exactly, exactly. So if A is in this group and B is some group which is very far off, let's say, let's say, let's say the minimum A and B are in these two groups. These two groups are arbitrarily far off. As the difference between A and B is arbitrarily large. So if we take the minimum element in this group and the maximum element in this group, f of A is at most the maximum element, and do you see the maximum element in this group will be m plus 2014 times the number of groups in between, and the minimum element will be small m plus 2014 times the number of groups in between, because the group, this group, the group on the right will just be the group on the left, but 2014 times something is added to each element, as we have seen here. 2014 is added. 2014 is added to each element. Is this fine? Now we have f of b is less than equal to is, sorry, is greater than equal to the minimum value in its group. With this hashtag is arbitrarily large because the groups are arbitrarily far. So what this gives, and these two are equal, what this gives is m plus 2014 times this hashtag less than equal to f of b equals f of a equal less than equal to capital M. But drawing this hash big, we are done. This gives a contradiction. So we get f is not injective. because F is injective. F is not injective gives a contradiction, and the only solution is 1007. Is this clear? Any doubts? Cool. So this was the first problem. I like these problems because you get non-standard solutions. Standard functional equation just involves plugging things, but this requires some thinking. Any doubts? Please feel free to ask. Otherwise, I'll move to the next question. Okay. So, the next question. Okay. What is not showing? Yeah. Okay. So this time we have a real to do. Positive reals, positive reals functional equation. So any guesses for the function? One guess is pretty obvious.
Constant solution to
Yeah, constant solution. The solutions is constant solution. And give you till 7:55 to make some progress. Hey Mohammed, if you have done the problem before, Mohammed Imran, let's not spoil it for the others. No problem. I'll probably write up a problem for you to try. If anybody has seen the previous problem, they can try this one. Ah, all the problems I'm doing are famous, so probably you've seen them now. I'm in 11th. LHS is symmetric and the RHS isn't, so we write another equation. The cancellation trick, okay? So you mean to imply force x equals x plus y f of x or y equals x plus y f of x. Clearly x can't be equal to that. So we try to force y equals x plus y f of x. I mean, we'll see. I don't know. Maybe it helps, maybe it doesn't. I'm just collecting thoughts, penning them down. This is x. Y equals x over 1 minus f of x. This can only work if f of x is less than 1 because we have the function, excuse me, we have the function equation from positive reals to positive reals, so y can't be negative. Y can't be negative. Only works if f of x is less than equal to, is less than, strictly less than 1. So this means if f of x is less than 1, putting y equals this value will get us equals to. Why? Because f of y and f of x plus y f of x come equal, so they cancel out. But this is a clear-cut contradiction because first we assumed f of x is less than 1, and now we are proving f of x equals to. Okay, f of x equals x plus 2 works. Cool. Ah, does it? Maybe not. We have a factor of 2 here. Factor of 2 messes things up. That doesn't work, I guess. Anyways, so f of x can't be less than 1 for any x. Because if it is, we follow this procedure. We put y equals x over 1 minus f of x, and we get f of x equals 2, which is false. So we get yeah, it does, it does. Let's see. Let's see how the question unfolds. F of x equals cx plus 1 for any c. Okay, try that. The factor of 2 here for some c. Okay, we get this. Factor of 2 messes things up. Hamiltonian on a dodecahedron. Probably you have unmuted mistakenly. Abhay, can you mute him? Hamiltonian on a dodecahedron. Hamiltonian path. Okay, sure. So we get this thing. Now let's put x. So this this thing seems very intractable, as someone said earlier. So we get f of x greater equal to 1. So probably we'll just bound this with 1. F of x, f of y equals 2 times f of this thing is greater equal to 2. 2. Now put x equals y and we get another inequality. But why stop here? We can replace that ugly thing on the right hand side with this, with root 2 now. 2 times, I'll probably write root 2 as 1 half. And putting x equals y and taking the square root gives us this thing for all x. So do you see the pattern? Here it was 2 to the 1 half. Here it was 2 to the 1 half plus 1 fourth. Doing this once again gives us f of x, f of y equal to 2 times this thing, which is 2 to the 1 plus 1 half plus 1 fourth for all x. We'll first put y equals x and take the square root. Oh, sure, sure. Do tell me. This is my solution. This may probably be different. So, do people see where this is going? By induction, we can prove f of x greater equal to 2 to the 1 half plus 1 fourth plus so on 1 over 2 to the I. For all x in reals, positive reals, for all I in natural numbers. You can easily formalize this, but due to lack of time, I'll be leaving that part to you. What does this mean? What does this thing translate to? For any I, this holds true. Exactly. Thing in the power can get arbitrarily close to 2 and it is always less than 2. This is standard. So on. Geometric series equals to the infinite geometric series. This thing is, if we cap this at 1 over 2 to the I, we get 2 minus 1 over 2 to the because taking this minus 2 to the 1 over 2 to the I to the left hand side, we get 1 over 2 plus so on minus 1 plus 2 this thing is I minus 1, then this thing, we reduce the power, there is a 2 to the I minus 2 here, that gets doubled and reduce the power, we reduce the power, and so on. So in the end, it's just 1 half plus 1 half, which is 1. Oh, sorry, it's 1. 1 half, so on, till 1 over 2 to the equals 1 minus 1 over 2 to the. So f of x greater equal to 2 to the 1 minus 1 over 2 to the for any n. So this thing can be made arbitrarily small. So in the limit, f of x greater equal to 2. Is this fine? If this doesn't strike you, assume f of x is slightly less than 2, but then making I large, we get this thing arbitrarily close to 1. So 2 to the circle thing gets arbitrarily close to 2. So for some large I, the thing, power thing, will get greater than 2 minus epsilon. Having this thing is powerful. The original functional equation was we can write this as a fraction. Okay. What can you say about f of I over 2?
Greater than or equal to 1.
Greater or equal to 1. This means f of x is less than equal to f of x plus y f of x for any y. So making z equals y f of x, fixing x and varying y, y f of x spans the whole positive real. So we get f of x less than equal to f of x plus z, which means f is non-increasing. I would have liked it to be strictly increasing, but what prevents us from doing that is f of y can be equal to 2. In that case, this equality would hold. Equality right here. The equality right here. So let's assume it holds. That is f of t equals 2 for some t. For any thing below t, t minus something, that is less than equal to f of t, because f is non-increasing, equal to, but this is also greater equal to greater than as we have deduced earlier. So anything less than t is also equal. Now putting x equals to t in the original equation and y, varying this from the open interval 0 till closed interval t, we get both of x and y are less than or equal to t, so that f's will be equal to 2. F of x equals 2, we get f of x plus 2y equals y ranges from 0 open interval 0 to t, so x plus 2y ranges from open interval x to 3t. Ah, this is t. Sorry. So t plus 2y ranges from open interval t to closed interval 3. So if on the number line 0, 0, everything less than or equal to t, if t, f of t equals to everything less than or equal to t has an f equals to 2. From there, we deduce that everything less than or equal to f less than or equal to 3t has an f equal to 2. From there, we deduce everything less than or equal to 90 has an f equal to 2. So this goes on and on and on, and we cover the whole real line. We get f of x equals to for all positive values. I'll give you a minute to think through this. Okay, so probably this is clear for people. Any doubts? Okay, I guess not. So if, so what do we get? We get that if f of t equals to t for any t, f of x equals to for all x intervals. So this was the function we guessed earlier. Now assume f of x not equal to 2 for any t. Now we can get the strict inequality. The strict inequality. Strictly greater than. This means f is strictly increasing. But remember earlier, this symmetric relationship. Do people get how we get a symmetric relationship? That's just putting y instead of x and putting x instead of y. The left hand side doesn't change, but the right hand side swaps its x's and y's. We have this thing, these two things are equal. So f plus f of x plus y plus x f of y. But f is strictly increasing. Oh, sorry, this is not decreasing. F is strictly increasing. If these two things inside the brackets were not equal, because this thing is less, this thing, the thing on the left is less than the thing on the right. F of the left thing would also be less than f of the right thing. So for them to be equal, for the f's to be equal, the things themselves have to be equal. Any doubts? So now this gives us x minus y equals x minus y. Sorry. X 1 minus f of y equals y 1 minus f of x. For any two x's and y's. So this becomes a constant. Yeah, you can fix y now and vary x, or fix x and vary y. So this becomes a constant, which implies 1 minus cx is f of x. So putting, I mean, minus c plus c hardly matters. So x equals cx plus 1. But putting this in the original equation, where was it? Here. Putting this here, as we saw earlier, gives a contradiction. So this doesn't work. And we have exhausted all the cases. So we can safely say the only solution to the equation is f of x equals 2 for all x in positive places. For all x greater than 0. Is this clear? Give you guys a minute to digest the solution. as it is, I'm running out of time, so I'll give the remaining problems for you to try. I'll briefly walk you through the solution once again. At first, at first, we notice the symmetric relationship. We swap the x's and y's. Then we try to force y equals x plus y of x. Y to the thing in the right. That gave us a clear contradiction. So, and provided us with the useful fact that f of x greater or equal to 1. Here. From this, we deduce that f of x is greater than or equal to root 2. From there, we kept on going and we proved this result. F of x is greater than or equal to half plus a fourth plus so on till 1 over 2 to the n. This in the limit gave us f of x is greater or equal to 2. Then we took two cases. If f of t equals to 2 for some t, and if f of x is not equal to 2 for all t. The first case gave us the solution f of x equals to 2 for all t. The second case gave us this solution from which we obtained a contribution. The other problems are long too, so I'll not have enough time to discuss them. But I'll put them. And all functions from z to z satisfying. The chat went too far. Yeah, Mohammed, this is Camo 2022 problem 2.
Hey.
I won't be able to comment on the Lebesgue theorem as I have not studied that much calculus yet. This problem, and then so this is it. I'll end the class here. Thank you all for attending.